We often say, the Sun is an average star, an unremarkable pinprick of light among the 100 billion in the Milky Way. But that's not quite right. The Sun is above average. A truly average star is smaller, cooler, and redder than the Sun, a red dwarf. Most of the nearest stars are in this category. For example, Proxima Centauri, our nearest neighbor at 1.3 parsecs, is a red dwarf. It's only 15% of the Sun's size. Another famous one is Barnard's star, only 1.8 parsecs away and 20% the size of the Sun. There are also larger stars. Although they're rare, they stand out because they're so luminous. Sirius is the brightest star in the sky. It's twice as massive as the Sun and 25 times more luminous. And Sirius is dwarfed by Aldebaran, the brightest star in the constellation of Taurus. The biggest star you can see with your naked eye is Betelgeuse, the star at Orion's upper left shoulder. It's about 1,000 times larger than the Sun. So if we swapped the Sun for Betelgeuse, it would engulf all the planets out to Jupiter. All of these stars are powered by nuclear fusion. But despite the common power source, stars show a wide range of properties. Remember the Hertzsprung-Russell diagram, where we plot luminosity against effective temperature, and by that strange tradition, we plot the temperature axis backwards? It shows us stars ranging in luminosity over 6 orders of magnitude. We also learned how to tell the radius of a star from its location in this diagram. The radius increases as we go from the lower left to the upper right. The important thing in this diagram is that there are patterns. There are giant stars, and there's a main sequence. For the stars on the main sequence, we observe that radius is approximately proportional to mass, and we observe that luminosity increases as mass cubed. In this lecture, we'll come to understand these relationships, and in the process, we'll learn more about how stars work. I'll start with a question. Why doesn't the Sun collapse? It's so massive, 2 × 10⁻30 kilograms. That produces an intense gravitational field. So what stops it from collapsing into a black hole? Maybe it is collapsing, but just takes a long time. The Sun is big after all. The radius is 7 × 10⁻11 meters. Let's calculate how long it would take for a sphere of mass m and radius r to collapse under its own gravity. Consider an atom at the surface. At time 0, gravity pulls inward, imparting an acceleration of gm/r². As time goes on, the atom falls to a radius r of t. The entire mass is also contracting, so the mass m pulling on the atom is always the same. But since r is decreasing, the acceleration is increasing. Acceleration is the second time derivative of position. So we need to solve the second-order differential equation for r, and then find the time it takes for the atom to reach r = 0. What's that? You're not in the mood to solve a second-order differential equation? Well, neither am I. So let's do what astrophysicists love to do. We'll perform an order of magnitude estimate. Let's use the letter big T to represent the time to collapse. And instead of trying to solve for r of t, let's replace the functions on both sides of the equation with simple expressions. Expressions that we have reason to believe have the right orders of magnitude. On the left side, we have acceleration. What's the typical acceleration of the falling atom? We know the average speed must be r/t, because it travels a distance r in a time t. But acceleration is the change in speed. Well, the atom starts from rest and reaches the average speed somewhere along the way. We don't know where exactly, but maybe we won't be so far off if we assume that it's at time t/2. That implies an inward acceleration of magnitude r/t divided by T over 2, or 2R over T squared. Meanwhile, on the right side, we have Gm over little r squared. Let's replace that function with, say, the value that it takes at the halfway point, when little r equals big R over 2. By making those substitutions, we've converted the differential equation into a simple algebraic equation, which we can solve for t. The answer is the square root of r cubed over 2gm. As usual, we use squiggles instead of equal signs to indicate this is only meant to be accurate to order of magnitude. I know from experience that this kind of ruthless approximation will rub some of you the wrong way. It seems like cheating. This kind of thing would never fly in a calculus course, but it's an important part of becoming an astrophysicist. And if you do take the time to solve this problem exactly, you get t equals pi over 2 times the square root of r cubed over 2gm. So we were only off by a factor of pi over 2. The order of magnitude calculation worked. Let's evaluate this free fall time for a sphere with the sun's mass and radius. We get about half an hour. So if gravity were the only force acting, the sun would collapse into a black hole in half an hour. That's not very long. So how does the sun survive for billions of years? It's because there's a force that opposes gravity, the force that arises from differences in pressure. The pressure of a gas is the force per unit area produced by all the microscopic collisions with the gas particles. When gravity tries to compress a sphere of gas, the contraction brings the particles closer together, increasing the rate of collisions. And the contraction releases gravitational potential energy, which heats the gas, making the collisions more energetic. Both of these effects cause the interior pressure to increase, leading to a net outward force that eventually becomes strong enough to oppose gravity and halt the collapse. The equation that expresses that balance between pressure and gravity is called the equation of hydrostatic balance. Hydro because it was originally conceived to understand water pressure. In fact, let's derive it in that context. Let's think about water pressure in the ocean. The pressure at the ocean floor is higher than it is at the surface. So pressure isn't just one number, it's a function of height, P of z. Now, consider a horizontal layer of water at height z with an infinitesimal thickness dz and a cross-sectional area A. Let's calculate the gravitational force and the pressure forces acting on the water in this layer. Gravity pulls down with a force dm times g, where g is little g, the gravitational acceleration near the surface of the Earth. And dm is the mass of the infinitesimal layer, which we can also write as density times volume, rho times a dz. Calculating the force from pressure is a little more complicated. The water in the layer feels inward pressure from every direction. The horizontal forces cancel out, though. The right side gets pushed just as hard as the left side. But the vertical forces don't cancel, because the pressure goes down with increasing height. The pressure on the top face is weaker than the pressure on the bottom. So the net effect of pressure is an upward force given by the difference in pressure, P of z minus P of z plus dz, times the area, A. If the water isn't moving, if it's in balance, then the downward force of gravity must equal the upward force from pressure. This leads to an equation in which the a's cancel out, and we can rearrange it into a suggestive form. P of z plus dz minus P of z all over dz equals minus rho times g. It's suggestive because we recognize that in the limit of small dz, the left side becomes the derivative of p. And that's the equation of hydrostatic balance. dp dz equals minus rho times g. For stars, we need to make a few changes. One of them is trivial. We need to replace z by r, the radial coordinate. More important is that when we consider a whole star, the density and the gravitational acceleration are not constants. They vary from the center to the surface. So rho becomes rho of r, and little g is replaced by the more general formula, big G times m over r squared. A subtler point is that m is now a function of r as well. We'll write it as m sub r. It represents all the mass located interior to r. That's from Newton's theorem. We only need to consider the interior mass when calculating the force from a spherically symmetric object. M sub r grows from 0 at r equals 0 to the total mass of the star when r equals the stellar radius, big R. Now, let's use the equation of hydrostatic balance to estimate the Sun's central pressure, Pc. In the spirit of order of magnitude estimates, we'll replace the derivative, dp dr, with a simple ratio, Pc over r, with a minus sign, because the pressure decreases from Pc to nearly 0 as we go from the center to the surface. And we need to replace the function on the right side with an expression representative of the value of the function. So let's replace rho of r with the average density. And for little r, let's use half of the total radius, and for m sub r, half of the total mass. That turns the differential equation into an algebraic equation, which we can solve for Pc. When we plug in the Sun's mass and radius, and its average density of 1.4 grams per cubic centimeter, we get 5 times 10 to the 14 newtons per square meter. To put that into perspective, that's 5 billion times higher than the air pressure here on the Earth. Next, let's estimate the central temperature, Tc. The temperature of a gas is closely related to pressure, as encoded in the ideal gas law, P equals nkt, where n is the number of particles per unit volume, k is Boltzmann's constant, and T is the temperature. We'll make one cosmetic change. Instead of number density, we'll write it in terms of mass density, rho, since that's what appears in the equation of hydrostatic balance. The relationship is simple. Number density equals mass density divided by the average mass per particle. Now, let's go. The ideal gas law tells us that central pressure equals central density times K times central temperature, divided by m average. And we also have our order of magnitude expression for central pressure that we obtained from the equation of hydrostatic balance. So let's set them equal. That leaves us with an equation where on one side we have the central density, and on the other side we have the average density. Those aren't necessarily the same. So what do? We make an educated guess. The central density is higher than average. Maybe it's twice as high. When we replace rho c by 2 times rho average, the rho's cancel out, and we can solve for Tc. Time to plug in some numbers for the Sun. The only thing we don't already know is the average mass per particle. For simplicity, let's say the Sun is made purely of hydrogen, and it's hot enough to be ionized, so there are equal numbers of protons and electrons. Both particles contribute to the number density, but the electrons have essentially 0 mass compared to the protons, so the average particle mass is half a proton mass. Plugging that in, along with the mass and the radius of the Sun, we get Tc equals 1.2 times 10 to the 7 degrees Kelvin. Hey, that's the same order of magnitude that we found in the last lecture to be sufficient to ignite hydrogen fusion. That's when the protons have enough kinetic energy to overcome their electrical repulsion and approach each other to within a de Broglie wavelength. So everything's hanging together. Isn't it wonderful? that we can deduce the conditions in the core of the Sun based only on its exterior properties and the observation that it's not collapsing. Although I should acknowledge, some of our approximations were pretty coarse, and the Sun isn't a perfectly ideal gas. In an ideal gas, particles interact only through collisions. There are no long-range forces. But protons and electrons do have long-range interactions, electric and magnetic forces. Officially, that makes the Sun a plasma, not a gas. Whenever I say that, it brings to mind one of my favorite bands from high school, They Might Be Giants. They played a song called Why Does the Sun Shine?, which starts, "The sun is a mass of incandescent gas." But then somebody told them about all the long-range forces, so they wrote a follow-up song called Why Does the Sun Really Shine? And it starts, "The sun is a miasma of incandescent plasma." Anyways, as it turns out, throughout the Sun, the kinetic energies of the particles are larger than the electromagnetic energies of their interactions. So for our purposes, it actually is reasonable to treat it as an ideal gas. Let's now get back to understanding the properties of main sequence stars. The formula we just derived for the central temperature was based only on the requirement of hydrostatic balance and the ideal gas law. That means it's true regardless of the source of the star's energy. The meaning of the equation is, you'd better have a source of energy that can keep the core at this temperature, or else the star will collapse. That's how the astrophysicists of the 19th century knew the central temperature of the Sun even before they understood nuclear fusion. We do understand fusion, though, and we saw that one important aspect of thermonuclear fusion is that the reaction rates increase rapidly with temperature. For each reaction, there's a sharply defined ignition temperature. An implication is that we should expect all hydrogen-fusing stars to have the same central temperature, regardless of the mass or the size of the star. And why is that? Imagine the birth of a star. A diffuse cloud contracts into a denser sphere, converting gravitational potential energy into heat. Once it contracts enough for hydrogen to ignite at the center, the resulting heat allows the star to achieve a balance between pressure and gravity. And this is a stable situation. If the star were to contract further, it would heat up, and the nuclear reaction rates would go through the roof, producing lots of pressure that would resist the contraction. So once a star achieves hydrostatic balance, the central temperature always hovers just above the ignition temperature. That's why, for stars fusing hydrogen in their cores, Tc is roughly a constant, independent of m or r. So our equation now says m over r is proportional to a constant, or equivalently, r is proportional to m, which is just what we observed in the chart of radius versus mass for main sequence stars. So now we understand the reason for that pattern. It's because main sequence stars are all fusing hydrogen at their centers. Let's not rest just yet, though. What about the other observed pattern between luminosity and mass? The data tell us that L goes as m cubed. How can we understand that? Well, if we make the usual approximation that stars radiate nearly as black bodies, then L equals 4 pi r squared times sigma T effective to the 4th power. So how does that depend on mass? We know R is proportional to m, but what about the effective temperature? It's important to remember that the effective temperature is the temperature of a star's outer layers, the photosphere, not the center. On the main sequence, the central temperatures are all about the same. They're all around 10 to the 7 Kelvin. But the effective temperatures are not. They range from 3,000 to 30,000 Kelvin. To understand the relationship between the central and the effective temperatures, we need to think about how the energy flows from the center to the surface. The fusion reactions produce very energetic photons, X-rays and gamma rays. But they don't make it very far because the sun is opaque. It's optically thick. This is because the interior is dense and because it's ionized. Charged particles, especially the electrons, interact strongly with photons. So the photons are nearly trapped. They transfer their energy to the surrounding gas, heating it up. Photons are constantly getting scattered, absorbed, and re-radiated with different energies. But the energy doesn't stay in the core forever. That's because the temperature can't be a constant throughout the whole star. The core is super hot. And above, the photosphere is the cold vacuum of space. So the temperature must be a function of R. And heat will naturally flow from high to low temperature, from the core to the photosphere. The rate of the heat flow depends on the temperature gradient. The larger the difference in temperature between the core and the photosphere, the more rapidly heat will flow. What happens is that the temperature gradient rises until the rate of heat flowing upward and escaping is equal to the rate at which energy is being released by fusion. At that point, a star achieves a steady state, and T of R stops changing. To be more quantitative, we'll model the heat flow as a diffusion process. We'll assume that heat is being transferred in the form of photons, but the photons can't travel far. They're like pinballs bumping around from particle to particle. Each time the ball hits a bumper, it collides and flies off with the same speed in a random direction until it hits the next bumper. After the first collision, it follows a straight path represented by the vector r1. After the second collision, it advances by r2, and so on. So after the nth collision, the location of the ball, r, is the sum of r1, r2, r3, and so forth, all the way up to rn. Now let's imagine playing a zillion pinball games. What's the average distance the ball goes after n collisions? To calculate that, let's square the equation for r. That is, we'll take the dot product of r with itself. When we expand that product, we get the sum of squares of each r vector, plus all the cross products, 2r1.r2, 2r1.r3, and so on. Here's where it gets interesting. All the dot products average to 0. That's because the vectors have random directions. Any two vectors are just as likely to point in the same way as opposite ways. So each dot product is just as likely to be positive as negative, and the average is 0. But the r squareds don't average to 0. They do have the same average value, since the bumpers have random locations. The average of each of the r squared terms will be the square of L, the mean free path. And since there are n terms, the sum is n times L squared. Taking the square root, we find that the distance from the origin, the so-called root mean squared distance, is equal to the square root of n times L. The distance grows as the square root of the number of collisions. Let's rewrite that in terms of the elapsed time, t. The number of collisions, n, equals t divided by the average time between collisions. And the average time between collisions is equal to the mean free path divided by the speed of the pinball, which is c, since the pinball is standing in for a photon. The distance grows as the square root of L times c times t. Contrast this to the case of a ball rolling in a straight line without any bumpers. The distance would be proportional to t, not root t. The dependence on the square root of time is a distinctive feature of diffusion. Now, back to the stars. What if the sun were optically thin, a transparent sphere of radius r? In that case, the photons could fly free and unimpeded all the way from the core to the surface. The the time to reach the photosphere, let's call it T free, would equal R over C. For the Sun, that comes out to be 2.3 seconds. But real stars are optically thick. The photons have to play pinball. To see how long that takes, let's take our diffusion formula and set the root mean squared distance equal to the stellar radius. Solving for t gives the diffusion time of r squared over LC. To evaluate this for the Sun, we need to know L, the mean free path. That's not something that we're equipped to calculate from first principles. We would need to consider every possible interaction between a photon and the surrounding particles, and then calculate the total probability for any of those incidents and accidents. That's a job for a quantum mechanic with a good computer. The outcome of those calculations is that the Sun's mean free path, averaged over its whole interior, is about 1 millimeter. If we insert the Sun's radius for r, and 1 millimeter for L, and the speed of light for c, we get a diffusion time of 50,000 years. That's an astonishingly long time. The energy that was liberated by nuclear reactions back in the last ice age is still reaching us today. And if for some reason the Sun's core emitted a sharp pulse of heat lasting only a second, the extra energy from that pulse would dribble out into space over tens of thousands of years. The lesson is that a star's opacity dramatically slows the progress of photons and spreads out their arrival times relative to the case of zero opacity. The ratio of the diffusion time to the free-flying time is R over L. For the Sun, that ratio is of order 10 to the 12, a trillion. And now we can understand the connection between the central and the effective temperatures. Here's how it goes. Imagine a hypothetical transparent star in which photons fly unhindered and rapidly deposit nuclear energy throughout the entire mass of gas. Every second, a certain amount of energy is liberated in the core, and photons spread that energy throughout the interior with minimal delay, bringing it all to the same temperature as the core. Now, that doesn't make much physical sense, but hypothetically, such a star would have a luminosity, let's call it L prime, equal to 4 pi r squared times sigma Tc to the fourth. In contrast, the luminosity L of a real star in which photons have to fight their way out will be lower than L prime by a factor of L over R. That's because the energy released each second emerges from the surface over a time range that's longer by a factor of R over L. So the energy per unit time coming out of the photosphere is lower by a factor of L over R. We also know the luminosity of a real star is equal to 4 pi r squared times sigma T effective to the fourth power. By setting those two expressions equal, we find the desired relationship between the two temperatures. Effective temperature equals central temperature times the fourth root of L over R. For the Sun, that's the fourth root of 10 to the minus 12, which is 10 to the minus 3. Nice. Not only do we understand why the Sun's core is of order 10 to the 7 degrees, that's when nuclear fusion becomes possible, we also understand why the photosphere is 1,000 times cooler. It's because the Sun's radius is 1 trillion times larger than the mean free path. Now we also have all the tools we need to understand the mass-luminosity relation. We've just shown that the luminosity of a star, L, is 4 pi r squared times sigma Tc to the fourth times L over R. Let's study this equation to see how L should vary with the star's mass. Tc does not vary with mass. It always hovers just above the hydrogen ignition temperature. So the only things in the equation that depend on mass are R and L. And how does L, the mean free path, depend on stellar mass? All other things being equal, it should vary inversely with density. make the star twice as dense, and a photon propagating through a certain volume of the star will encounter twice as many obstacles and will only get half as far. So L goes like volume over mass, r cubed over m. Altogether, we expect L to be proportional to r squared from the area times r cubed over m from the mean free path divided by r. And we already know radius is proportional to mass, so we can replace the r's by m's in our proportionality, leading to the conclusion that luminosity is proportional to mass cubed, which is what we observe to be true for main sequence stars. Well, I don't know about you, but I think we've made a lot of progress. We understand why main sequence stars with different masses have the sizes and luminosities they do. It follows from a few physical principles. Hydrostatic balance between the inward force of gravity and the outward force from the pressure gradient. The ideal gas law. The very sensitive dependence of thermonuclear reaction rates on temperature. And the concept of radiative diffusion, the fact that stars are opaque to their own photons, drastically slowing their progress from the core to the surface. We managed to do all this in 30 minutes by limiting ourselves to order of magnitude calculations. This is a helpful approach to gain an understanding of the basic physical principles, but a certified stellar astrophysicist needs to actually solve the differential equations using detailed models for the nuclear reaction rates and the transfer of energy, which, by the way, can also be carried by convection in addition to radiation, a possibility that we ignored for simplicity. Let's peek at the results of those detailed models for the Sun. Here's the temperature as a function of distance from the center from the so-called standard solar model. Our order of magnitude approach couldn't tell us the shape of this function, but it did tell us correctly that the central temperature is of order 10 million degrees. As for the density, the mean density is 1.4 grams per cubic centimeter, but in the standard solar model, we see the actual density ranges from around 150 at the center to nearly 0 at the surface. This next one I find especially interesting. It shows the composition of the Sun as a function of radius. Out at the surface, it's basically 75% hydrogen, 25% helium by mass. But the core is different. It's only 35% hydrogen and 65% helium. That's from billions of years of fusion. The Sun has been converting hydrogen into helium, steadily depleting the hydrogen in the core. Our next goal in this course will be to venture away from the main sequence and ask, what happens when the core of a star runs out of hydrogen fuel